Okay, Math 113, we are on to part 3, and definitely the last part of our vectors video. I'm going to see if I can explain this well enough and knock this stuff out in a short period of time. We've got application problems to do, and you know how that goes. Sometimes it's a little bit detailed and takes a while. Now, in the end of part 2, we were given some scenarios and asked to write a vector to represent that scenario. And what we did is we used the fact that V is equal to the magnitude of V, because they gave us a magnitude, times cosine of theta times the I vector, which is the unit vector in the horizontal direction, plus the magnitude of V times the cosine of theta. I did it again. Y'all just paid attention to the last video. I accidentally did that. I did fix it. So you saw me fix it if you're patient enough to wait around. All right, so that's what we're dealing with. Now, in this particular situation, example I, we're trying to find the magnitude V and the direction angle theta for the given vector. So it's almost like it's backwards. They're giving us the vector, and we've got to work backwards to find the magnitude and the direction angle. Okay? Now you already know how to find the magnitude. We did that before. So the magnitude of V, remember the wild absolute value bars, there we go, is the square root formula-wise of A squared plus B squared, where A and B are the component values of the vector. So AI plus BJ. That's just general formula right there. For our particular problem, the magnitude of V is equal to the square root of A squared, so negative 3 squared. Remember, the I and the J do not go in this calculation. Okay, if I simplify that, that's going to be the square root of 9 plus, what is 16 squared? If you said 256, you are the winner. Okay, so 9 plus 256 gives me 265. And I've got to take the square root of that. And I am pretty positive that 265 is not a perfect square. Now, notice our favorite directions ever, round to the nearest hundredth and the nearest tenth, respectively. So hundredth was magnitude. So when I type that in my calculator, I get 16.2788206. Again, round to the hundredths place. So that's going to give me approximately 16.28. And my units, we don't have any units. Okay, if this was a true application problem, we would have pounds or miles per hour or whatever the situation is, but all we have is 16.28. Okay, now how are we going to find the direction angle? Any thoughts about that? Well, you know the deal. You know the story. Tangent of theta. Tell me about tangent of theta. So tangent of theta is equal to y over x. That's just the general formula for tangent of theta, right? Well, we have a y component and an x component. So how about we use that? Tangent of theta is equal to y, which is our b value, over x, which is our a value. Another way to think about that is sine of theta over cosine of theta. That works, doesn't it? So you're going to have to use your inverse tangent button. So theta is equal to the inverse tangent of b over a. And again, our b is 16, our a is negative 3. Now, you got to be careful with this answer. Okay, so let's see what we have. Calculator. Now, did it say degrees or radians? It doesn't. It just says to the nearest tenth. Most of this work that I have found has been in degrees, so I'm going to leave my calculator in degree mode. 16 over negative 3 is not a standard value in the unit circle, so radians, you know, let's just go with degrees. So inverse tangent, there we go, of negative 16 thirds. Going to get negative 79. Now we'll take this on out a little bit. Negative 79.380 degrees. My answer is not supposed to be negative. Remember, the direction angle is supposed to be between 0 and 360 degrees. We also have a second issue, is that tangent is negative in two different quadrants. How did I know my answer is in where this is versus the other quadrant? So let's draw a picture to see what we've really got going on here. Okay, now negative 79.380 degrees. You go backwards with the negative angle, right? That's right down here somewhere. Ooh, I drew that horribly. So that is negative 79.380 degrees. That's what that is. But is my vector down here in quadrant 4, where tangent is negative, or is my vector in quadrant 2, where tangent is also negative? And how do we know? Remember, there's two different locations where tangent of theta is equal to negative 16/3. Well, how about this? If we graph negative 3i plus 16j, I'm going to graph that guy in green really fast right here. Y'all, negative 3 is the x component, 16 is the y component. That looks more like that. This guy's in quadrant 2. So our problem is the vector really lives up here, and this is the angle that we're looking for. How are we going to find that? Okay, well, symmetry-wise, how about this story? This angle right here, if that is negative 79.380 degrees, then this is also 79.380 degrees from 180 degrees right there. It's symmetry. Okay, so to find my angle in green, which is really my answer, I'm going to do 180 degrees, right at the bottom, minus 79.380 degrees. I sure hope that made sense. Remember, when you calculate or when you find angles using inverse trig functions, it's only going to shoot out one answer, depending on the domain and, well, really the range of the inverse trig function you're using. But the correct answer for whatever problem you're dealing with, there could be two different options that are correct. And so, for one thing, you can't use a negative angle, but that's not even our total problem. The other issue is what quadrant are we in? And if you graph that vector, you realize that's in quadrant 2. So we need the vector that's in quadrant 2. We need the angle from the positive x-axis to that value. And again, that's going to be 180 minus 79, which is just a hair over 100, right? So 180 minus 79.380 equals 100.62. Now, the reason I took that out a little further than the 10th place it asked for is because I knew that wasn't my final answer, and I like to take it out a little further until I'm done. So how about 100.6 degrees? That is my theta, which is my direction angle. Okay, so be really careful with that. Okay, I've got 3 more decent-sized problems that I want to do. 1 discussion page, and that's it. But this is going to take a few minutes, so bear with me. The magnitude and direction of 2 forces acting on an object are 70 pounds at south 56 degrees east, and then 50 pounds at north 72 degrees east, respectively. Okay? Find the magnitude to the nearest hundredth of a pound and the direction angle to the nearest tenth of a degree of the resultant force. Okay, remember the resultant force means we're adding these two vectors together, but we need them in vector form before we can easily add these two vectors together. So there's some things that we need to be thinking about. So I want to draw just an XY axis to talk about bearing. So you remember north, south, east, west. So our first vector at 70 pounds is south 56 degrees east. It means you go south first, and then you go 56 degrees towards the east direction. So that's going to look similar to this. I'm not trying to be exact. That's what we have going in bearing form. Okay, and if you want to write the magnitude next to the vector, sure, go ahead right there. But that is not your directional angle, right? It's not. all we know is that we're 56 degrees off south in the east direction. Your direction angle, I'm going to draw this in green, is that guy right there. Okay, so what is the degrees? Well, we know we have, remember that's 270 degrees going from the positive x-axis, which is the east direction, all the way to the south direction. So that's 270 degrees plus 56 more degrees, and y'all know I'm so calculator dependent, I don't even want to give myself a headache thinking of that, is 326 degrees. Okay, so instead of using south 56 degrees east, I'm going to use 326 degrees for the 70 pounds of force. Now, let's think about this again for the next vector, okay, the 50-pound magnitude vector. We're going north 72 degrees east. So again, north, south, east, west. If you struggle with that, I know some people do, write it down every time. So we're going north first, and then 72 degrees in the east direction. So something like that. So this is the 72 degrees. That is also not our direction vector. Our direction vector is supposed to go from the positive x-axis, which is the east direction, up. How do we calculate that? Well, we take the 90 degrees, that is that entire first quadrant, and subtract out 72 degrees, and that's going to give us our answer of, watch this, watch that work in my head, 18 degrees. I sure hope that's right. It's right. Don't worry, it's right. Okay, so that's 18 degrees right there, 18 degrees. And remember, if you want to write that force right on top of it, that force was 50 pounds. So instead of using north 72 degrees east, I'm going to use 18 degrees as my directional angle. Now, I've got to write each of these vectors in that IJ form. Okay, I'm going to call the first vector V, the one I worked in a lot of green, and let's call the second vector W, just to make things clear. So my V vector is going to be 70 times the cosine of, remember our directional angle is 326 degrees I, plus 70 sine of 326 degrees J. Okay, now my vector W is equal to, that's 50 pounds, and that is going to be cosine of 18 degrees I plus 50 sine of 18 degrees J. Now remember, the resultant vector, we add these vectors together. Okay, so we can do that right down here. Now, you can't just add 70 plus 50 is 120. You know it doesn't work that way. I need to type all this in my calculator. Now, here's where I get bothered by the directions. It says, find the magnitude to the nearest hundredth of a pound and the direction angle to the nearest tenth of a degree. Oh, it doesn't say anything about rounding on this one. I'm sorry. There's a problem that I'm going to show you in a minute. It says don't round until the end, but it's a whole lot to keep up with your calculator until the end. This one doesn't say anything about that. I'm just going to take it out a little while and try not to do a lot of rounding until the end. So my resultant vector, so I'm going to type this in my calculator, 70 cosine of 326 plus 50 cosine of 18. You pause it and do that yourself. Now, when I did that calculation, please make sure you're in degree mode. I got 105. I'll take it on out a little ways. 5,855. That's farther than it needs to be taken, but I always do that until the end. Okay. Plus, now I'm going to do it again. 70 times the sine of 326 degrees plus 50 times the sine of 18 degrees. In my calculator, pause it, see what you get. Okay, and I actually got a negative, so I'm going to get rid of my big plus sign that I have a habit of writing down. So minus 23.6927 J. Now, what am I supposed to do with that? That's my resultant vector, provided I typed in everything correctly and analyzed these angles correctly. But they want us to find the magnitude to the nearest hundredth and then the direction angle. And now we are where we were in the last problem. So to find the magnitude of my resultant vector, y'all, let's just call that guy R for resultant vector. It's going to be the square root of 105.5855 squared plus 23.6927 squared, all underneath the square root. So the magnitude of my resultant vector, in my calculator, I have 108.2110883. Remember, that was in pounds. Now, careful, rounding is said to the nearest hundredth. So my magnitude is actually 108.21 pounds. Okay, not finished yet, but I'm halfway there. Now we are asked to find the direction angle. Okay, so we have tangent of theta. Remember, that's y over x or sine over cosine. So that's going to be negative 23.6927. Oh, no, my battery's running low. No! Hold on, I gotta plug her up. I'm back. The magic of pause. Okay, so again, let me highlight for you. This was our resultant vector, right? That's what I called R, vector R. Now, if I'm doing tangent of theta is equal to the y component over the x component, or the sine value over the cosine value, I'm right in the middle of that, negative 23.6927, that's my sine value, divided by my cosine value, 105.5855. Now, remember, this is kind of the scary thought of this. There's going to be two different quadrants where tangent of theta is negative. How do I know it's negative? Well, this negative divided by this positive is clearly negative, right? So my answer is either in quadrant 4 or quadrant 3. Now, y'all come over here to this top XY axis I have drawn that I'm circling. I don't know if you can see that notation or not, but I'm looking right here inside the green box. Now, we know quadrant 4 down here, bottom right, quadrant 2 way over here. That's where tangent's negative. Now, where's my resultant vector going to be if I have a vector in quadrant 1, which is the bottom vector, and a vector in quadrant 2 added together? Well, it can only end up in quadrant 1 and 2. There's no way that thing's going to turn backwards and end up in quadrant, I said that wrong, 1 or 4. There's no way it's going to turn backwards and end up in quadrant 2 or 3. Does that make sense? So I know my answer has got to be in quadrant 4. And it's a lot to think about. You got to know a whole lot of trig really to think that through. But again, tangent's negative in quadrant 2 and quadrant 4. But when I look at these vectors, there's no way my answer is quadrant 2. Another way to think about it is my x component, my horizontal component is 105. Way out here, my y component is negative 23 down here. Clearly in quadrant 4, right? So I know when I finish this up, I need a positive angle in quadrant 4. So I'm going to type this in my calculator. I'm going to pause it so you don't have to bear with me while I get it typed in. You do the same thing. We'll see if we get the same answer. Okay, so when I typed it in, I got negative 12.647 degrees. Now remember, I'm not supposed to have a negative direction angle, but hey, that is in quadrant 4. So how do I write that same angle that's negative 12, that's the negative 12 part, as the direction angle that starts here and goes all the way around? Well, how about I do 360 degrees minus that 12.647 degrees. I'm going to leave you on while I do that. So I get theta is equal to 347 point, now rounding, where else is it round? 1/10 of a degree. So that's going to be 4 degrees, because mine says 347.3526962. So 347.4 degrees. What you think? Is that all right? I hope so. All right, let's try another one. Let's see how we do. Now I'm going to be honest with you about K. It is very similar to what we just did. Did I call that the right? Yeah, I called it J. I was worried that I didn't call it J. So K is very similar to J. All right. You could get away without doing K. I picked both because I think students find this stuff incredibly confusing. So if you feel like you need another example, here it is. And this represents the homework very well as things stand currently. So I've got the magnitude and direction exerted by 2 tugboats this time, towing a ship, are 4,200 pounds at north, 65 degrees east. First, let's represent that in terms of compass directions. Okay? How about my pen's not working? Let's try it again. There we go. All right, so I got north, south, east, west. And so this 4,200 pounds is north first, and then I turn east 65 degrees. So basically about there. That's the 65 degrees. There is my vector, and the magnitude of that dude is 4,200 pounds. Now, is 65 degrees my directional angle? No, it is not, right? Because I need this angle from the positive x-axis, which happens to be the east direction. How am I going to find it? Well, we know this entire quadrant adds to 90 degrees. So if I do 90 minus 65, yes, I really am typing that in my calculator. I know better, but I did it anyway. So it's 25 degrees is my directional angle. So instead of using north 65 degrees east, I'm going to use 25 degrees. Okay? Now let's do the same type of thing down here for my other vector. This guy's at 3,000 pounds, and it's at south 58 degrees east. So again, north, south, east, west. If you struggle with that, do it every time. Okay, label them. So south first, and then I go 58 degrees in the east direction. So basically, there's my 58 degrees right there. Again, is that my direction angle? Why is that not my direction angle? Because your direction angle starts at the positive x-axis and goes to meet the vector right there. That's my direction angle. How do I find it? Don't I just do the same thing I did last time? 90 minus 65 or 90 minus 58? No. If you'll notice, this is 180 from here to west, or you could say it's 270 from east all the way down here to south, and then add the 58 degrees. So that angle is going to be 270 plus 58 more degrees. That I do want to type in my calculator. And I get 328 degrees. That is my directional angle. So instead of using south 58 degrees east, which is bearing, I'm going to use 328 degrees. And at this stage, keep yourself organized. So I'm going to call that first vector V that I did in green, the second vector W that I did in purple, and then we'll call R our resultant vector. How's that? So I'm going to write the green one first. So we have 4,200 times the cosine of 25 degrees I plus 4,200 sine of 25 degrees J. Okay, that is my vector V. I didn't give myself enough room to write the V. And then in purple, I got my vector W, which is equal to 3,000, because right there, 3,000 cosine of 328 degrees I plus 3,000 sine of 328 degrees J. Those are my two vectors. I like to line them up vertically because I'm adding them together and I'm getting a resultant vector. I'm just going to call it R. Now, the directions on this for the one that shows up in the online homework is a little bit sticky. It says, do not round until the final answer. And then in addition, I put watch your rounding place value. I asked you to round to the nearest pound and then the nearest tenth of a degree. In the homework, it might ask you to round to the nearest hundredth of a pound. It just varies. This problem came out of the textbook, whereas rounding in the homework is different. So be very careful about that. But I'm going to tell you the truth about this. Do not round until the final answer business. I struggled to get all this mess typed in my calculator without rounding. Because remember, the final answer isn't this resultant vector right here. The final answer is the magnitude and the direction angle. So if I can't round, then keep in mind, I'm adding these two together right here and squaring it. I'm adding these two together and squaring it, and then taking a big square root of all that, because that's the magnitude. It took me 5 times typing in the one that's in the homework into my calculator to get it right, because there's parentheses all over the place. So y'all, what I'm going to do on paper is what I did on the last problem. I'm going to not square, I'm going to do magnitude in a minute. I'm going to type in 4,200 times the cosine of 25 plus 3,000 times the cosine of 328 degrees. And just take it out a little further. Maybe take it out 4 decimal places. And then put an I next to it. And do the same thing and put a J next to it. I'm going to shut up and do that right now and pause it. You do the same thing and let's see if we get the same answer. Alright, check out these numbers. So again, make sure you're in degree mode. Most calculators, you'll type in 4,200, hit the cosine button. What's going to happen is a parenthesis is going to pop up right there in your calculator. You need to close the one after it. And then hit the plus button, and then do 3,000 times the cosine. Again, a parenthesis is going to pop up automatically for you. And you're going to type in 328 degrees. You need to close out that parenthesis after that. You might have to push enter, and I got 6,350, and then it kept going. I went out 6 places. Actually, I went out 5 places, didn't I? 0.63699. Okay, here again, 4,200 times the sign, a parenthesis will pop up. You close that thing out. If you don't close that out, you're going to have a problem. Okay, this one especially. Okay, plus 3,000 sign, that one's going to pop up. You want to close that one out also. And I got 185.23891J. Okay, that is your resultant vector in terms of I and J. Now, we're supposed to find the magnitude of this resultant vector, which requires us to square that number. It's a lot to write. 6,350.63699 squared. Okay, plus 185.23891 squared. Now again, this one says round to the nearest pound. The one in the homework, I think, says round to the nearest hundredth, or at least one of them does in the homework. And it also says to not round until the end. But trust me on this, just take it on out way past where it says to round. If it says to round to the tenths, you may even want to take it out 6 or 7 places and do your calculation. Unless you are super comfortable with all those parentheses, you would have to type in the calculator. Now, when you type this in, square plus square, and then take the square root of that entire result, you get 6,353.33, keeps on going. I'm supposed to round to the nearest pound, so 6,353, what's happening, computer? 3 pounds, okay? That is your magnitude of your resultant vector. And then finally, we're supposed to do tangent of theta. Remember, sine of theta over cosine of theta, or you can think about it as x over y. That's going to be tangent of theta is equal to, so this is your y value, 185.23891 divided by 6,350.63699. Again, I took it way out because I want to avoid rounding issues. Okay, now it says that I can round to the nearest tenth of a degree for the degree, so let's type this in. Now, I do sincerely apologize for some of this impossible to read, but again, this is this number right here, 6,350.63699 down here, and I want to type that in my calculator, so I'm typing in inverse tangent of that fraction. Okay, now what I got is theta is equal to, what popped right out of my calculator is 1.67076. It keeps going. Okay, now remember tangent of theta, this is positive. It's positive in 2 different quadrants. This answer could be in quadrant 1 or it could be in quadrant 3 where tangent is positive. Now if you look at my vector right here, this is huge. My horizontal component is positive. My vertical component is positive. We're talking about in quadrant 1. This is degrees. Is that in quadrant 1? Well, sure. It's so tiny. It's only 1.67076 degrees. It's super tiny. That is in quadrant 1. I'm supposed to round to the nearest tenths place. So my theta would be 1.7 degrees. Okay, so a magnitude of 6,353 pounds at 1.7 degrees is my directional angle. Okay, so there's 2 of those problems. Just be careful. I don't find it difficult. I find it tedious. So make sure you follow the steps. Be careful typing things in your calculator. I've got one more problem to do for you. I've passed my 30-minute mark, but I'm going to keep on going because we need to wrap this one up. So this is the last problem that I've got for you, okay, and then something to just discuss after that, and we're going to call it done. So it says the figure shows a box being pulled up a ramp inclined at 18 degrees from the horizontal. So this is the 18 degrees that they are referring to, okay, and this is very much like a problem that you might do in a physics class, okay. Notice BA, okay, so the directed line segment, which is a vector, BA, which is straight up and down, vertical is force of gravity. That makes sense, right? So if this is the ground across the bottom here, then gravity is perpendicular to the ground, so pointing straight down. Okay? Now, the magnitude of BA is the weight of the box. Remember how I told you weight is really mass times acceleration? Okay, so the weight should be pointing in that same direction, but your weight is just going to be the magnitude of the box. So they're not saying it's a vector, it's just the magnitude. Okay, now AC, where's AC? You see that across the bottom? It says the magnitude of AC is the force needed to pull the box up the ramp. Okay, so whatever that force is, that's how much we need to pull the box up the ramp. You notice it's at the same angle as the rope and the incline pulling it up the ramp. Okay, BC, where's BC? Okay, that is perpendicular from the base of the box down. That's the magnitude of the force of the box against the ramp. Okay, so that's the box pushing against the ramp. All right, now it says if the box weighs 100 pounds, so remember the 100 pounds is weight. So that's the vector, which one? What is the 100 pounds? Is it BA? Is it the magnitude of BA? Is it the magnitude of AC? Is it the absolute value of BC? By the way, I do believe they're missing some wild vertical bars there. There we go. Because it says it's the magnitude, so they need those double vertical bars, don't you think? Okay, so back to the question. If the box weighs 100 pounds, where's the 100 pounds go? Okay, well, they tell us that that's the weight of the box. Right there, that's 100 pounds. So if I were to label that, let's make this triangle bigger. Might not look just like this one, but it's going to be bigger. They tell us that that's 90 degrees too. Mine doesn't look very 90, but we're going to say it is. Okay, so that's 100 right there. They tell us that this is 18 degrees inside. Notice that matches our incline right there. It's almost like this triangle is just turned upside down. Okay, what are they asking? So if the box weighs 100 pounds, find the magnitude of the force needed to pull it up the ramp. Remember, they told us the force needed to pull it up to the ramp is BC. And they even highlighted, they did red for us. This is what we're doing. We've got to find that value right there. Okay? Turns out this is not as vectory as some of the other problems. What can we do? How about we just use some trig to find out the length of this side? Because it's asking us the magnitude. It's not asking us to write the, excuse me please, it's not asking us to write the vector in component form or anything. It's just asking the magnitude. So what is the length of that side right there? How are we going to do that? Okay, well, you remember across from the 90 degrees, we call that the hypotenuse, right? If this is 18 degrees straight across from there, that's called the opposite, which means this leftover guy that we don't care about right now is called the adjacent. Now remember how to solve triangles? I hope you do, because this is one of the most important things you do in a trig class. If you have a 90-degree angle, remember, you want to use the side that you know, so we need a trig function with hypotenuse in it, and the side you're looking for. We need a trig function with opposite in it. Somebody holler out real loud so I can hear you. What trig function has opposite and hypotenuse in it? I did hear you. Sine, yes, you told me sine. So sine of theta, remember, is equal to opposite over hypotenuse. All right, got it. So I've got sine of theta is equal to the opposite. That's the guy we're looking for. If you wanted to call it AC, the magnitude of AC, you go right ahead. If you just want to call it opposite, I'm cool with that. Over the hypotenuse, which is 100. Oh, I forgot to put the angle in there. Let's back up. I don't want to put theta in there. I'm going to put the angle in. What's the angle? 18 degrees. So how am I going to solve this trig equation? I'm going to multiply both sides by 100. So the magnitude of AC is all by itself. In my calculator, I'm going to type in 100 times the sine of 18 degrees, and that's going to be my answer. And when I did that, actually I hadn't done it yet, hold on. Sine of 18 degrees. I've got 30.90169944. Way too much. You don't need all that. If you read the directions, it doesn't tell us where to round, does it? I hate it when that happens. So if the box weighs 100 pounds, find the magnitude of the force needed to pull up the ramp. So let's round to the hundredths place. We have to make that decision on our own. Okay, so how about the magnitude is going to be 30.90 pounds. What you think? You like it? All right, so that's your final answer. I've got one more thing I wanted to discuss. It's not a regular problem. It's just an idea to help you with other word problems you may run into. This is just really cut and paste from the textbook. I thought they did a good job of it. Their drawing was great. I just went with it. It says many physical concepts can be represented by vectors. A vector that represents a pull or a push of some type is called a force vector. So if you're pulling up a cart or you're pushing a lawnmower, let's say, those are force vectors. If you're holding up a 10-pound package like this lady is over here, okay, picture that a 10-pound box, okay, two forces are involved. The force of gravity, of course, is pulling the 10 pounds straight down. That's your F1 force. Okay. On the other hand, this lady is working to oppose that force, and that's the F2 force going upward. It says, assuming there's no upward or downward movement, so she is completely still. Okay. You are exerting a force of magnitude 10 pounds directly upward, just like we said. The force is shown by vector F2. It has the same magnitude as the force exerted on the package in the opposite direction. Now, here's the trick, okay? If F1 and F2 are two forces acting on an object, the net effect is the same as if just the resultant force F1 plus F2 acted on the object. If the object is not moving, as the case with your 10-pound package over here, the vector sum of all the forces is 0. Okay, so if we added F1 plus F2 together, you would get the resultant force, and that would be 0 if there's no movement. Now, this is not this picture over here, but let's just say we had another force, F1 of 3I minus 5J. That's at an angle, clearly. Okay, then if we had F2 is negative 3I plus 5J, that's in the completely opposite direction, right? So that would give me 0I plus 0J as the resultant force. That's no movement, right? So it would just be exactly the opposite. And again, if and when you take a physics class, you will see this. And then the final comment that I want to make is I typically don't do this, but I know you saw Pearson written at the bottom of several of my slides, not of all of them, but I just did not want to teach this section by drawing a lot of my own figures. I liked their figures, so I used Pearson. We used Pearson as a textbook, so it's perfectly fine, but I do want you to realize that I copied some of Pearson's free and offered PowerPoint slides to get the job done. I hope you have a wonderful day. If you have any questions about this or any other sections, please let me know.